Hello everyone. Today we will be learning how we can fit a simple linear regression. There could be many types of regressions modeling, but we will only learn about how we can develop a simple linear regression. That means basically we need to find, given a data set, what will be the mathematical straight line so that we can show the relationship between two variables. So let's actually draw. So let's say I have two variables. Let's say one variable could be height of trees, and then dBH, the diameter of trees, dBH. If I have some sample data set, then you will see that I can find the data point somewhere here, maybe here, maybe here, maybe here. Then you can see that there is a trend of this data set. So that means if dBH increases, height is also increasing. And in simple linear regression, what we try to see is that what's the trend we have, whether we can develop a line, let's say the line from here, so that we can capture what is happening within the data set. And why we want to do that? Let's say our sample data stops here, but if we want to know further, then we can extend the line and then we can find the relationship, and then we can say that if we have certain number of dBH, the dBH values, then what would be the future height? That's what we cannot get from the data set, right? Or let's say in the middle of your data set, if we have a gap, let's say dBH value, some value, we don't have the height. What would be the height for that dBH? We can also find that using that relationship. So that's why we would like to develop a model, a linear regression line. So there are many, you will see that many models in forestry for volume, biomass, or below ground biomass, and then we can develop those model, and then we can find the equation and then find the future estimate, or maybe the previous, or maybe in between. Another reason is that sometimes you will see that the variable we are looking at is really expensive, or let's say it's not possible sometimes to collect that. So let's say in a dense forest, sometimes you will see that it's difficult to find height, but it is easy to find dBH. Also for that reason, sometimes we just collect some samples, and then we develop the model using the sample data set, and then we just try to see if we have the other dBH values, what would be the height for that. So the objective we have in this lesson, you will see that we fitting a simple linear regression model and testing the significance of that regression, because what we are developing, is it at all meaningful? It has any significance? We will do a test. We learned before how we can perform hypothesis tests. So you will see that that's what we will be doing in here as well. And then we will try to calculate the confidence limit of the coefficients. I will talk about that, and the regression line for both. So we'll try to see what are the limits, the upper limit and lower limit. So I will show you some examples so that it might be helpful for you. So you will see that in a simple linear regression model, basically we draw this line. So you can see that the predicted y, that means the height value I was showing to you, what would be the future height maybe. So that we are trying to predict using the model. So in the model, we basically try to find what would be the start point and what would be the slope. Let me define from here. Let's say in a data set, when we have a data set and when we found all the values in the relationship graph, you will see that the data points are above or below. And then using the simple linear regression, we developed an equation. So it's a straight line. So where it's actually touches the y-axis, this is what we call intercept. That's it. This is where we are going to start. And then how much increment, let me actually draw here. So the data points, let's say data points were somewhere here, 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 or maybe here, something like that. And then using these data points, we found this straight line. Then I would like to know what is the slope. We found that we are starting from here, but when we try to find the slope, then what we need to do, let me actually erase all these values so that might be easier for you. So for the slope, what we need to do is that, let's say the DBH value, if DBH value increases from, let's say 10 to 11, DBH value was 10, now it increases to 11. For 1 unit increment in the DBH value in the x-axis, how much the height value increases. So that's what slope is. So you can see that it try to find the angle. So that means, let's say I try to find what's the height value here, and then what's the height value for 11. That means on your y-axis, how much increases. That's what we call the slope. So we will basically try to find what would be the intercept, what would be the slope. If we can find that, then using our DBH value, because DBH value will go in here, and then at first you have to use the intercept, that means where you are going to start, plus the slope, that means 1 unit increment in the DBH value, how much it increases in the height value, and then you have to multiply this intercept by the x value, that means the DBH. And then you would find that using this equation you can find any height information. But how far we can do that? We cannot stretch too much. We cannot stretch, let's say, way up here. There should be, usually we say that we can increase a little bit more than the data set, or maybe within the data set. That's we have to maintain. So you can see that in this lesson we gave you a data set, and then in the data set we have the tree volume, tree basal area. So I will actually show you all the steps using this data set in an Excel file. So in this data set we are thinking that the tree volume is difficult to find, and tree volume is our dependent variable. That means this is what we would like to predict, and then when we are predicting it, we are using this tree basal area as our independent variable. That means this is what we are going to use in our regression line. Our main interest is to at first find, are there any relationship? If there is no relationship, that means scatteredly it shows up anywhere, the data points. That means there is no relationship between volume and basal area. If there is a relationship, you will see there is a trend. You can see here is a trend. But if values were somewhere here, 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 then there is no relationship. So at first you need to find that. And then when we have the regression line, then you will see that if we have this regression line, then data points are above or below. How much difference we have from the equation to that data point, that's what we call error. That means that much difference we have. So these are the calculations we have to perform so that we can basically get the slope and intercept. That's what I would like to show you in an Excel file. I will show you using that example all the steps. So just like the ANOVA example I gave you, I at first tried to calculate all these, so you can see that, so that I don't need to, whenever I will be doing the complicated analysis or doing a lot more bigger calculation, then I don't need to calculate it again and again. This is how I do that, but you may have your own ways of doing it. So you can see that the tree volume data set and the basal area, at first you need to know what would be your independent, what would be your dependent variable. So in here, volume is my dependent variable and basal area is my independent variable. That means the volume we are going to predict using the regression line that we will be fitting. And you can see that at first I try to find what would be the multiplication of each of these values, that means 0.24 multiplied by 0.31. And then for each of those data points, I try to find what would be the multiplication of them. Then I sum them, sum of all the tree volume, sum of all the basal areas. So you can see that I find the sum of yi, sum of x and y. That means the sum of these values. I also try to find, if I take the square of each of these values, there's a 0.24 square plus 1.64 square, then what would be the value? That means sum of squares I try to find for both of these variables. I also find what would be the mean value of y, what would be the mean value of the independent variable. So you can see that. Then we are fine. We don't need to worry too much. And then you can see I also at first try to see if I plot the observed so that whether I can see any relationship between them. If I plot volume versus basal area, you can see that yes, definitely there is a relationship going on. Okay, and then we would like to find where we should start, what would be the slope value for them. To do that, our main interest is to find this regression line. Okay, to find this regression line, what we need, you can see that for slope we have to use this equation, and then for intercept we have to use the mean values that we found, and then what would be the slope. That means at first we need to find the slope. For slope, you can see that we need to get two values, the sum of the product and then sum of squares of x. So you can see that for sum of squares of x, sum of squares of the product, I found them separately. So at first I try to find what would be the sum of squares of y, because later on you also need that. Sum of squares of y, we found all these values already. So you can see the sum of squares of y squared, I already found it here. Sum of squares of y, sum of squares of y, and square divided by n. So that means these are the values I already found. For same thing I did for sum of squares of x using the values I found above. Sum of product, I also find the product value, and then sum of x, sum of y, we already have that over here, and then I just added them. That's how I actually calculated the slope and then the intercept. Then you can see that I found the slope and intercept. So that means if I take minus 0.31 plus 13.01 multiplied by the basal area, then I can get any value for the volume. That's the predicted value. So that's what I actually did. I used that equation, this equation that I just fitted, and then I took the data set. So you can see this is the data set we have, and then what would be the predicted value. And so you can see that I took, let me show. Okay, so you can see that I took the x value, and then I took the what x value was 0.31 multiplied by 13.01 and then plus 0.31. So that's how I calculated the other values. Okay, there was something wrong. So you can see for each of them I use this equation, and then I try to find what would be the predicted value. And then after I found the predicted value you can see it has a hat on it. That means I'm predicting it. What would be the difference between what we have in the data set, the volume we have, and then the predicted value we got? That means the error, the residual we have in the data set. So I found them as well. Okay, so that's how we can fit a linear regression line, and we can see the errors, we can find the prediction. Now the question is whether we can test if the linear regression is significant. That means what we develop, is it significant enough or not? That means the regression is not significant is the null hypothesis. The alternative is that it's actually significant. So that's what I tried to test. So using an ANOVA table, just like you did before. So you can see that I wrote down all of them. For regression, since we have only one independent variable, and then we have two items in the regression line, the slope and intercept. So that's why we have 2 minus 1. 1 is the regression degrees of freedom for the regression. And for error degrees of freedom is the sample size minus 2. We have sample size 10, and then sample size minus 2 you have to use. The sum of squares, so I will show you how you can calculate the sum of squares for regression, for the error, and how you can find the mean square. Mean square is easier, but then again, you also need to find what would be the F calculated value. For these two, if we can find these two and sum of squares of total, you can easily find that. Degrees of freedom is already defined. So for finding the sum of squares of total, then you have to use sum of squares of y. That means sum of squares of y you already calculated before using the y values. That's what we directly used. Sum of squares of regression uses the slope multiplied by sum of squares of product. That means sum of squares of product we found it before. And then sum of squares of residual, you just need to take the total minus the sum of squares of regression. That's how I found all these values, sum of squares of them. Mean square is just you need to divide 60.576 divided by degrees of freedom. Same thing for error, you have to take it and divide by the degrees of freedom. That's how I found mean square error. And the F calculated value is just the regression sum of square divided by the error square. That means the mean squared error. MS residual, what we call that. So we will be using all of them. So for finding the whether regression is significant or not, we need to find the F critical value. So F critical value would be you can use any level of significance, usually use 0.05. So that's what I used, and then I said the degrees of freedom is coming from the ANOVA table 1 and 8. So using 1 and 8, I found the F value would be 5.3. You can use that. So you can see that it's actually the F critical value is way higher than the F critical value. That means F calculated is in the rejection region. That means the regression is significant because it's in the rejection region. Finding correlation coefficient is way simpler. All you need to do is that finding correlation coefficient, you need to take you can see that the regression sum of squares, and then you also need to take the total sum of squares. That's how we can find that, the sum of squares for regression, sum of squares for total. That's how we can find the correlation coefficient. If you take the square root, then it will be your correlation coefficient. That means in the linear relationship we have, how much correlation is going on. So you can see there is a high correlation between them. So the correlation coefficient is R, and you can take the square root. And coefficient of determination is the just the, if you take the that's the coefficient, correlation coefficient. You already found that from the coefficient of determination. So in the coefficient determination, what we try to see is that if we have the regression line, how much we are defining using the independent variable we have. So that means the coefficient of determination is directly the, if you take the sum of square, that means how much you are defining using the independent variable. That means using this regression line, how much you are considering. So you can see that some of them are going to error. That means that much we are not defining. Okay, so standard error of estimate, if you take the mean squared, what you find in its residual, if you just take that and take the square root of that, you will find the standard error of estimate. That means this is measuring the standard deviation of the residual around the regression line. That means how far they are varying from the regression line. The standard error for slope, if we want to find the 95% confidence interval, we need that. So that means the standard error for the slope, we can just take the mean ms residual and divide it by sum of squares of x. Then you will find that that's the standard error for slope. So you can see I just directly use the two values from the table, and then I use that. And then this one is coming from the table, but this one you actually calculated before. And we need three values in our confidence interval. One is that what would be the slope we found, what would be the standard error of that slope, and what's the t value. That means the tabulated value. The tabulated value, level of significance, we have to use that. And what's the error degrees of freedom, n-2, we have to use it. So for 0.05 and 8 degrees of freedom, we found the value is 2.31. Then I just use that. So I say 13 minus 2.31 multiplied by this value is giving me the lower value. If I take, instead of minus, if I sum them, then you will see that the upper limit is here. So the slope is actually not including 0. That means actually at some value. Sometimes you can test using the confidence interval. So in the confidence interval, you can see that it's not including 0. That means the slope is significantly different than 0. That means it's not 0. That means it has some significance. 0 means it has no slope. That means the line is straight. There is no there is no slope in there. That means it's straight. But if there is no slope, that means it's a straight line, like that. Okay. And then similarly, you can also find 95% confidence interval for intercept. For that, you can see that we have to use this equation for finding the standard error of intercept. And then you can say I use the same t value. So for the t value, you have to use level of significance divided by 2, because that's the same thing you have to do in here as well. You can correct that, because we are trying to find on both sides. Then using this equation I actually use the ms raise from the ANOVA table. This one is coming from before sum of squares of x square, sample size minus multiplied by sum of squares of x. That's what I use from the table. And then the rest is easy. So all I did is that with my negative 0.31 minus 3.02 multiplied by this t value. That means you just need these three values so that you can find the lower value, and then upper value is easier, so you only need to sum them. Okay, so similarly you can also find 95% confidence interval for a tree volume. Let's say we are saying that we have a tree Basel area. For that tree Basel area, that means for an independent value, if I give you an independent value, the Basel area, then what would be the confidence interval for the dependent variable? That means for the volume we have. Then you can easily find that using the regression line. You can find for the independent variable variable value, what would be the predicted value? So I just try to find the predicted value. So you can see that I use the regression line and find the predicted value. Then for any confidence interval, we need to find the standard error of the estimate. The standard error of that prediction value would be this one. You already found all these values before. That's what I just plugged in. So you can see that. So that means the MS res and then 1 over n plus the x value you used. So you can see that the x value I used is 0.68 and then divided by SSX. That's what I used. And then that's the standard error for the prediction. And the t value would be same as before, the 8 degrees of freedom and then 0.025. And then if you use these three values, then you can easily find that. So the 8.5 plus or minus, depending on upper or lower value, t value multiplied by the standard error. Okay. Just I would like to show you, if I ask you to find, let's say, perform a test where the average volume of a tree with this, that means this is the independent variable value I gave you. I ask you to find whether this is actually significantly greater than 10 meter cube. That means the volume we are asking is more than 10 or not. That means that's for the independent variable. So we want to test whether the volume is 10, less than 10 or more than 10. And then less than 10, more than 10, that's our interest that we would like to find. But we need to find what would be the predicted value if we use the 0.68 basal area. So using the regression line, same thing, we did that. So we found that the volume is 8.537 using the regression line. And then what would be the standard error of the prediction? Same thing I used. So you can see that the standard error of the prediction, I used this same thing, same equation. You can use this same equation. You can see that MS res 1 over n and then 0.68 minus the mean value of the independent variable and then divided by SSX. And you also need to take a square and then square root of them. Same thing I did, same value I used. And then the test statistics is the t value. So the t value would be if I have this from the sample what I found minus the what I have in the hypothesis. So that's what I did. What I found in the sample minus the hypothesis value divided by the standard error. So the t value I found already, and then t critical value is you can say is a one-sided test, so based on the hypothesis, and then the critical region is 0.95. You can see that at that point what would be the t value using the 8 degrees of freedom, and then you can use 0.95. what's the value we have. Then you can see that it's actually it's actually not in the rejection region. So we cannot reject the null hypothesis. That means it's actually less than 10. That's what we also found in our sample. So you can see that I wrote it just like that. T critical value, and therefore cannot reject the null hypothesis. That means the tree is not significantly greater than 10. That means actually less. Similar item I did, another test I would like to show. This is the last test. So you will see that in this test, I said whether the intercept is significantly greater than 0. And then I might ask you the intercept, whether it is actually less than or greater than, the intercept will be 0. So I should use B0. Okay. So that means we want to find whether the intercept is less than 0 or greater than 0. For intercept, you have to use this standard error. I used this standard error, and then I found that standard error for the intercept is 0.3028. You can plug in all these values. Intercept we found from the regression line, and then using the calculated value, what you have to use is that what's the intercept you got, the value you got from your fitted line, and then what's in the hypothesis. That means 0.31 minus 0 and divided by the standard error. So we found that the value is negative 1.024. This is actually way less than the pre-critical value. Same thing happened, that means we cannot reject the null hypothesis. That means it's actually less than or equal 0. Okay, so that's about it. I hope this is helpful for you. Thank you. Thank you all.